I think we can start. Is that okay?
Yeah, sure.
Thank you everyone for participating here. Your presence in the energy system and network. We're going to start. I don't think Dr. Bashir is here, is it? No? No. Okay. We're going to start with our keynote speaker, Dr. Wei, professor in the Department of Engineering at King's College London. He's also a PI in the King's Sustainable Research Lab, and his areas of focus are the economic and implementation challenges in net zero transitions and sustainable development. Okay, it also includes grid-scale energy storage, consumer energy decarbonization, and flexible electrochemical processes, and the nexus and system approach. His presentation will be energy storage and flexible technologies for renewable integration and sustainability. Okay, Professor, the floor is yours.
Thanks for the introduction. Thanks for the introduction. So I'm Wei He. I'm from the Department of Engineering, King's College London. So as mentioned, so the topic I'll talk about energy storage and flexible technology in the context of energy system and the network. So, like within the decarbonization or net zero transition, there will be a lot of challenges around the temporal spatial variability and also the flexibility. So here's one example in the kind of typical like zero carbon net zero system using solar and wind. So there are some the different time scale require the energy shift from daily like several hours to like weekly, between 10 to 100 hours, and on a yearly, more than mainly for the seasonal energy storage or energy shift to support the balance, within a zero carbon system. And but also there at different location, that's mainly the first one mainly for the mathematical or like the energy balance perspective. For second one, you definitely have infrastructure transfer of energy from generation through the transmission distribution line to the demand. Depending on where you are, probably you also have limits or constraints, to limit what you can use and also how to use your energy storage or like different technologies. And the third one will be, we are all talking about kind of established national grid or energy system. There are also problems like off-grid system, or even like in rural area in developing country or in US or UK kind of developed country, that also like remote area, they need like off-grid or distributed energy system solution. So there are a lot of requirements for different, for solutions to address the temporal spatial variability induced by the renewable energy system. So our group focuses on like three focuses, mainly like two different topics. So first one, like we develop system approaches, energy system and the kind of network. So saying natural network, I'll give you some example. What do I mean by this? So we believe in the next transition. So electrical grid and renewable energy will be the fundamental sources to supply all other majorly supply all other infrastructure, like water system, like carbon cycle, and also like food supply chain and many other infrastructure or system we are currently using. So we want to understand how the interlink between the different systems and how we can use renewable energy to support other system transition, including the electrical or energy system transition. At the same time, we also look at can we leverage the other infrastructure to help balance the renewable energy. What I mentioned in the previous slide, like temporal spatial variability. So to improve the kind of cooperation between different systems, we also look at we call some interfacing technology. But basically, there will be something like energy storage, so you can store and convert the energy in different forms. You may also like carbon capture, which can link the energy system with a carbon like cycle or carbon capture or storage and utilization system. And also we talk about, we also study desalination, which can live with energy water system. We convert energy to fresh water or like hot, like agriculture water for different purposes. And also we look at the food cold chain, which link the energy of electricity with the energy required by the food. And then we also look at the consumer-centered technology like electric vehicle or heat pump, which link the electricity with transport and heating purposes. So we have all 4 other papers. 3 of them have been presented. Another one will be presented probably in about 10 or 20 minutes. So because all of them, they have clear link with different users, different stakeholders. We also want to, from a consumer perspective, to understand how we link better the technology with a potential user. So the overall objective for our research, we want to develop insights which can understand how to handle, and also same time we want to develop technology and innovations to support and accelerate the net zero transition. So by maximizing co-benefits across the systems, so reducing the cost. And one of the other very important point we are focusing on, we want to integrate the user preference or behavior or perspective into the technology design, try to increase the technology adoption to accelerate the transition. So because we have several other papers focused on different topics, so in this talk, I mainly talk about energy storage and the flexible technology for this sustainability in our group. So energy storage, so depending on the different status of the energy transition, so we even look at the duration of energy storage. So there's a paper try to show a different status. You may require the requirements for energy storage potential different. So we will have very relatively low, like the decarbonization or like the penetration of solar and wind in the grid. I mean, in theory, you don't need very long duration energy storage. You may need something around like 1 hour or 7 hour energy storage. But with increase the penetration of the renewable energy on the grid, for example, like in UK aims to have a low carbon or net zero grid around 2030 or 2035. So it means you probably need 80% plus renewable energy on the grid. During that time, you definitely need a lot of much longer energy storage to meet the energy system requirements or maintain the balance. So in this context, so longer duration, which need to deliver the energy storage over like tens of hours, hundreds of hours is greatly needed to ensure we can have a stable and reliable electrical grid, but with a highly penetrated renewable energy. So if we look at the different energy storage technologies in the literature, so it's a kind of based on the paper published in Nature Energy, and we also add some other data points. In there, if we separate all the technology into the typical, like short duration, which basically mainly on lithium-ion battery, electrochemical energy storage, and some other like mechanical energy storage, mainly have decoupled power and energy storage. So which means you have relatively low cost to store energy, and then you can potentially for longer duration. So that's kind of how normally in the literature we separate from observation or like by nature of technology, we can very high level can separate technology into two different categories. And they're arguably the $100 to $400 or pound per kilowatt hour potentially would be the like economic viable cost for short duration energy storage. So that's something like lithium-ion battery potentially is approaching that price point. But that's basically for the kind of daily operation. You probably use one cycle per day. So that means during a whole year, you provide service like 365 cycles of times. So when we talk about longer duration, so that means you probably provide one cycle per week. So that means you only have 50 cycles, like a year. If we talk about, even longer time, if like we probably anticipate the 1/10 of the duration, like 10-time duration requirement, like even 1/10 of the price point for the longer duration energy storage technology. So here are particular two technology we look at, because like as I mentioned, like for some of the technology here, one is called compressed air energy storage, the other called pumped hydro energy storage. So that all the mechanical energy storage, they have the type of power generation, which can be like turbine, or a compressor, or storage, it could be water reservoir or air reservoir. So they have separate units, so you can have different costs for different power unit and energy unit. So in this sense, when you have different storage duration, so that means like you have very large reservoir, which you can store a lot of energy, you have much volume of air or water stored somewhere, which can provide very long duration of energy. However, you have relatively small power unit, so then your power cost will be also relatively low. So depending on different duration, you may have different costs. So we found some data from the literature to show both technology potentially can have very low energy storage cost per dollar per kilowatt hours. And so we think like for mechanical energy storage, they have a great potential to be longer duration energy storage. So what we did, so basically, so what is compressed air? So that's one of the technology we are focusing on. So as I said, so it used to be, so it's not a new technology. So in the past, the first launched in 1970s, so in Germany. So basically, when you have off-peak electricity, so you use compressor to pressurize the air and store the pressurized air in some container or some underground caverns. And when you need electricity, you mix the compressed air with the gas turbine to increase the temperature. So you have both pressurized air and the high temperature pressurized air, which can produce more energy. But in a traditional system, it uses natural gas. But in the new context of the energy transition, so people want to get rid of the gas. So with the new technology called adiabatic, so that means it doesn't require any external heat. So in the adiabatic compressed air energy storage, so when you have electricity, you still use motor to drive compressor to produce pressurized air. Because the air pressure is increased, so the air temperature also increased. So in the adiabatic compressed air energy storage, store the heat and the pressurized air separately. So you let the heat stored in the thermal energy storage here to pump back thermal energy storage, and then you store the pressurized air in the air tank. So you can store all the energy actually from the converted by electricity into two different reservoirs. And when you need electricity, so you let the pressurized air be heated by the thermal energy storage same unit. So that means you still get the pressurized and heated air back. So you can go through a turbine to generate electricity. So the concept is quite straightforward. So it tries to mimic the traditional thermal engine process, using heat as the driving source to produce electricity. So during the charging, you store you create a thermal gradient, and the discharge process, you use the thermal gradient to produce electricity. So when I said we are developing the technology, so basically we look into individual components. We try to see, in the underground cavern, how the heat exchange of the air at different conditions, different locations, different forms of storing air, how it interacts with the environment, with the cavern, with the surrounding environment. We also do the very technical detailed simulation of the thermal energy storage, the thermal plant, the thermal distribution within the plant across different design. We look into turbomachinery design across different components, and we integrate them as a whole in the system. So I will not talk too much about technical details, but in general, what we are doing here, we try to understand how the design parameter of individual components to link with the overall system static and dynamic performance, which can help us to design individual components and according to some system level signals, like how we can, for example, if we want to let energy storage technology to participate in the arbitrage of electrical market, what should we do, which component we need to operate, which component we need to optimize, and how we do that is through the whole integration modeling framework we developed. And another example, like we also want to evaluate how the geological resources like underground caverns can support the large scale energy storage technology to decarbonize the energy system. So we look into the UK-based current gas storage facility, underground salt caverns. We map all the locations on the left-hand side. So like the yellow circle represents the different volume of existing gas storage facilities in the UK. And there's all the transmission line we built a model of the UK electrical system. And we also built all the power, like the power generation, including both gas power plant and the solar and wind into this power system model. So on the right-hand side, so which we actually have not considered in the model, but here the green area red indicate the potential resources available in the UK to have further caverns, for different type of gas storage. It could be used for like compressed air, hydrogen, or CO2 storage. But in general, the figure here, we did another kind of feasibility study. In general, in the resources available for example, in the UK, for underground salt cavern, it's much more than enough at a near future, or at least for energy transition, as far as we are aware. So saying that, what I mean, like there is no kind of competition between either cavern will be used for compressed air, or for hydrogen, or for CO2 storage. If you need, there are sufficient resources available, at least for UK. It probably will be quite similar in other European countries. So in our analysis, we basically, based on the existing caverns, we first indicate the potential energy storage using this cavern for compressed air. The energy storage capacity will be something around 800 gigawatt hours. It doesn't seem very large, but if you put into the UK context, we put, you probably know better, how significant or how insignificant it may be. So we built a model. So we use our energy system model, the UK scale system model. So we use 3 scenarios or 3 systems to evaluate how this 800 gigawatt hours may contribute to the different UK energy system decarbonization, because there are certain different caverns. They have different parameters of the volume, like pressure range and the flow rate, charging and discharging flow rate. So we also consider all those technical data into the modeling. So what we found, like depending on different, and also I want to mention it's a soft experiment. So in this analysis, we may assume the 2018 UK energy system with this compressed air energy storage. There are no other energy storage available. So 3 scenarios will be either the real or like almost the real UK system in 2018. Another scenario will be the low carbon UK energy system with increased generation from solar and wind without energy storage. The third one will be a exact same low carbon UK system with increased solar and wind with the 800 gigawatt hours like across certain storage sites. So the result tells like depending on different operational parameter and also storage parameter of the compressed air, the different side offer provide different energy storage for different duration. So for some like more efficient energy storage sites, they provide like daily storage, less than 1 day operation. For some other like less efficient due to the geometrical constraints or like the variables, they provide mainly longer duration energy storage. And so that's all depending on the parameters or like the specification of the caverns and also the operation parameters in the modeling. So overall, we compare the 3 different scenarios. So we can say the different function of the compressed air energy storage, because when you have different geometrical parameters, you have different performance, and increase and use the 800 gigawatt hours compressed air energy storage, it could increase the use of energy storage by reducing the curtailment by about 53% compared to the system B and C. Without energy storage facilities and with energy storage facilities. And the use of existing underground gas storage facility for compressed air and variable wind generation can reduce electricity emission by 85%, with about 28 cost increase compared to 2018. So we all know, in the last several years, because pandemic, because the war between Ukraine and Russia, so the energy price has been increased significantly. So all the costs we're considering here is a pre-pandemic cost, a pre-pandemic cost. So that means if we use current energy costs, potentially it's 28%, it's not so bad anymore. So we further increase the modeling capability of the UK, for example. Like we break the UK into 13, 12 or 13 regions, which align well with the distribution region in the UK context. And we try to develop a model to simulate, how the transition at different locations and how may understand which technology to use. So we have a particular focus currently. We try to see if we separate the technology of energy storage into different types, like which multiple short-term energy storage, like battery, lithium-ion battery, or some like more typical long-duration energy storage, like what I mentioned, like compressed air and pumped hydro, depending on if you have resources or not. So in the UK, like for pumped hydro, probably it's kind of saturated. So we mainly looking using the parameter of the long duration energy storage to represent the compressed air or many other similar long duration energy storage. So here is some preliminary results. So we're still working on that. But in general, we run different scenarios to see how this energy storage technology will be deployed to achieve at least the cost of energy system transition. So I think one interesting point through this process, what we really want to know is the emission induced due to the use of energy storage. So there are several concepts about the energy emission, induced by using energy storage. It doesn't seem quite straightforward, because we know like sometimes you can find a lot of headlines or like in literature, like energy storage is one of the key technology to help to enable the net zero or transition or energy system transition. But there are also another large amount of literature or papers talk about if you use energy storage, it will introduce more emission, from the grid. So the reason is like all the system currently we have, we use the mix of generation. If we only consider the operational generation, that means that if we assume like solar, wind, or some other renewable energy to be zero emission, for many other fossil fuel based, they have some positive emission. When you have the demand, like if we say it's original demand, but if we use, for example, and then at this time, if you turn on your energy storage, so that means you need the most flexible or dispatchable generator will need to be operated longer, like higher capacity, produce marginal generation. So that means, so depending on how you account this emission, sometimes there are two concepts often used in the literature. So one is called average emission factor. So that means the emission due to use of energy storage comes from average carbon emission of this snapshot generation snapshot, or they're called marginal emission factor, which is more about the marginal generators emission factor. So if you use the marginal emission factor, so that means the most likely the most polluting generator the electricity from most polluting generator will be used to charge the energy storage, and due to energy storage has some inefficiency, which is not 100% efficiency. So compared to now use, the energy storage and the using energy storage, again, the scenario with energy storage will induce more emission. So we feel like both average emission factor and the marginal emission factor may not be perfect to describe the what will be emission due to the use of energy storage. Because for the energy storage, sometimes it's not about marginal, because it's not about the marginal 1 kilowatt hours or even 1 megawatt hours. It's also not about the average, because compared to the peak or the total generation power, the energy storage probably only a small fraction. Depending on different, from now to future, even in the future, if majority to have very large scale energy storage, it's still just a fraction of the generation. So we try to develop a more kind of duration, between the two, which is more accurate to capture the cycle emission factor. So depending on how you operate the system, in each of the cycle, we want to calculate the emission per cycle. So it's not necessary to be a full cycle. So we want to let the storage technology into the system. We use model to optimize how to use the technology to achieve the least cost, and then we back calculate what will be the per cycle emission factor, in this whole year out of this simulation and optimization. So similarly, here are some preliminary results. Because they are all preliminary results, I don't provide too much details, but in general, here, like every point here, so every color represents one region, and the top one is the battery, which we say short duration energy storage. The bottom one is the longer duration energy storage. And the different color represents the energy storage at different nodes or different location in the electrical network. So basically, the results indicate for short duration energy storage per cycle, the emission per cycle is relatively higher compared to all the energy emission, cycle-based energy emission, from all the longer duration energy storage. So, and that means like, if you have longer, so that also gives you some idea how this duration affect the emission related to the different operation of energy storage system. So another very important point is the cost. So I did mention the cost of energy storage in my first several slides. So this is the paper I mentioned earlier. So it's a paper published in Nature Energy in 2017. So if you work on the energy storage, probably you notice this paper many times. So basically, using learning curve to understand or to forecast future costs of different type of energy storage technologies. So in this one particularly, you can find a downtrend curve, so which indicate the cost of, for example, lithium-ion battery at different application like utility or like electric vehicle application keep decreasing with the increase of the capacity accumulation. And the same group of authors, they take this approach and project the cost reduction of the different type of energy storage. So here you can see, for example, for the lithium-ion battery, so they project from 2050, if they say it's 100% of cost. So the 2050, it will reduce only 14% of the 2015 cost. But if you look at the pump hydro, so they project the cost will be increased by 2%, but they assume the pump hydro will be nothing to learn, and also with inflation, whatever reason, the cost will increase as well. So they also assume the compressor area will be same as pump hydro, because by nature it's a mechanical energy storage. So similarly for hydrogen, so the cost reduction from 2015 to 2050 about from 100% to 33%. So this is their assumptions or parameters used in their analysis. So and then they look into different types of the electrical services. Basically, you can find in the 2015 scenario, so the majority of the energy across the different, hour per discharge and the discharge per year. So this the bottom line here will indicate the frequency of the use frequency of the technology, and this one more about the duration for one full discharge. And you can find for most of the main duration, if we call this one the short duration, this one long duration, something in the middle we call mid duration. The majority of the energy storage application for duration in the main duration, it will be provided by the pump hydro energy storage and the compressed air according to the 2015 cost and performance parameters, and only a little bit the very long duration provided by hydrogen, and short duration provided by a mix of lithium-ion battery and the flywheel probably, and another one is purple will be the flow battery. But if you use the same approach but change the parameters of the technology in 2050, so the hydrogen, start to occupy the space of mid duration from long duration, and the lithium-ion battery, also become more cost-effective in most of the, probably half of duration according to this wide scale. So the results tend to be, so I think the author probably use the way like compressed air being compressed, so it lose the cost effectiveness, within the middle. So from kind of the clear kind of the range to almost nothing here. So I mean, I totally understand and agree the approach to use, but I think the key here, like the parameter, I want to mention the parameter clearly make a role to determine which one will be the best technology or least cost technology in future system. So I would say like we try to fill the gap of the data and knowledge on the cost of compressed air. So which means that we try to look into literature and also other reports to see if compressed air is quite similar to the pump hydro, because there is no potential to reduce cost, or it will be quite similar to lithium-ion battery, which can still learn and learning by doing through the renovation research to reduce the cost. Because if you still remember, at the beginning, I mentioned that compressed air, there are a lot of new operation, new technology compared to traditional technology. So for the thermal energy storage, for the high pressure turbine machinery, there are a lot of, it's still quite, new technology, or quite a lot of research challenges need to be overcome. So we found like in the most of pilot demonstration project and in the literature, the cost reported by the authors or by the owners of the project keep decreasing, from about with the increase of the capacity installed across the world. So there's also some ongoing work. But here I want to highlight. So the parameters in the energy model and the network modeling and optimization, the cost parameter play a major role to determine which technology could be the better technology in the future scenario. However, the visibility or availability of the data, cloud technology is entirely different, which may also affect, decision making or policy making, even the investment decision making. So we should, try to keep the, all the options available and then to have more comprehensive assessment. So that's what we want to do. We will try to improve the data and can provide more insight on this particular technology. So the second part, I'll talk about the flexible demand. So in this particular case, we focus on off-grid solar desalination system. So try to address the water shortage and the climate, like a transition problem. We want to the sustainable energy provide very needed water for particularly for developing countries. So the technology we are using called electrodialysis is an electrical chemical process. So basically it has electrode with cathode, anode, and turn you have several pairs of ion exchange members. When you apply electrical field, and because the selectivity of the membrane, so the cation exchange membrane only allow the positive ion to pass, and the AEM only allow negative ion to pass. So as a result, so all the ion pass to the ion in this channel, transport to the channel next to, and then nearby, and then this channel, the cell will be depleted with the flow passing through the flow channel, and this channel become more and more concentrated. So you have a water flowing out with lower concentration, have another channel have a higher concentration. So that's an electrical chemical separation process using exchange membrane as well as external electrical field. So in this particular technology, so the energy consumption, including both the voltage or like the energy due to the voltage applied on the electrodes, as well as the pumping power to pump the water going through the membrane channels. So put the diagram into the practical system. So here is a commercial available electrodialysis stack. So they here have around like 60 or 80 pairs of membrane. You have an electrode on the two sides of the stack. So the reason we choose this technology because it has very high recovery ratio, so about 6 to 80. So this means the 60 to 80% of water from the saline water will be converted to the fresh water. Only 40 to 20% water will be. So the dilute water will be the 60 to 80%. The concentrated water will be the 40 to 20%. And in some low concentration, which kind of underground freshwater desalination, it has higher energy efficiency than the most. They are the filtration-based air produce reverse osmosis as a benchmark to justify why this technology has the potential energy efficiency. So this is but what we are proposing actually is very straightforward as well. We try to improve the flexibility of using the ED technology. So the first idea, like we want, because of the product of this technology is produce water rather than produce electricity. So in an off-grid system, normally we use battery, to provide to balance the solar energy availability or intermittency to ensure the energy supply to meet the demand of desalination and produce water. But the battery it's relatively expensive, which require high capex, and also because it also requires kind of maintenance effort, it makes it challenging in off-grid regarding the remote area. So some, and also because it's very expensive of battery in the kind of off-grid rural context. So sometimes you may have very limited capacity of battery. You may have some solar curtailment, and also overall, it may lead to high cost. So what we propose, like we add a water storage, which is very simple, like water bottle, water tank. Because we need to produce the water is your only product. Instead of to store electricity, just store water. And you can reduce the capacity of battery, which can reduce the cost. So we take the concept into the system of design, and we try to see if water storage can be equivalent to battery storage to produce water to meet the water demand. So without changing anything else, we're just introducing one more component, which is also very simple and a low-cost component. So we found like we're using water storage potentially can reduce the battery storage capacity, and we can reduce the cost of 45% over the lifetime. So this is actually very straightforward because like you probably do it every day, if you want to. In some other similar cases. But the very interesting result from this experimental or pilot testing is like, so in an optimal system, so no matter you use both water storage and battery storage, so we still have a 46% available like the solar energy, when unused. So the reason is mainly due to the balance between the solar, like intermittent solar generation, and also the cost to store in the battery storage. So you want to have so if you increase further, if you want to reduce the redundancy or like unused solar energy, you probably want to increase your water storage or increase your battery storage, because due to some like the water quality reason, we have an upper limit for water storage. So that means mainly if you want to use more, increase efficiency of solar energy here, you may want to increase the capacity of the battery. However, because the battery or the relationship between the PV cost and the battery cost is so different, so the optimal result would be waste of 40% or like 46% of solar panel and only store a little bit solar in the battery. So That's a practical, cost motivation or cost economic reason to kind of make the solar energy utilization relatively low. And also because this ED demand is quite static, so we want to use it as long as possible. So it's also without a longer work days. So now we try to, in addition to using water storage as flexible solution, we also want to use to make the demand to be very flexible. So that means like we can try to increase the water production rate without using battery. So we can try to use the 46% unused solar energy, and also we can reduce the work time and also minimize the battery storage. So we do the modeling optimization. Also, we also build a system to validate or demonstrate the performance of the concept of the flexible operation of the ED system. So roughly here, here is the result in a 1 day, of solar day performance. So because some of them it's also already exceed the maximum power available from the ED system. But if within a range of the operation, it can closely follow the solar power, and no matter how fluctuated it is. So the one key innovation or research we showed in this research, like we not only make it flexible, but at the same time at different level we also maximize efficiency, at the same time. So it's not only about we just change the power to match the solar availability. We also, in theory, we ensure at different levels we can achieve the maximum efficiency. So as a result, so we reduce the solar energy utilization, or we increase solar energy utilization to 76%. If you still remember that previous one, about it's like 40, like about 50 something efficiency, and we can reduce the battery storage capacity from about like 4.75 kilowatt hour to about just like about 0.25 kilowatt hours. And also we did the testing across different days. We have the very cloudy day, a very clear day, clear sky, the day with sunshine and clear sky. So, and then we found like no matter how fluctuating the solar power is, the system can consistently produce the water amount of water required for according to the production rate. And if the daily energy available from the solar is similar, water production rate is also similar. So that means the system can be producing water independent of the fluctuation of the solar power, mainly based on the energy available from the solar. So it's when it becomes very flexible. So we put everything into the technical performance and the operating time, so it can reduce so that increase the solar energy utilization, reduce operational time, and reduce the battery. If we put everything into the cost, so if we compare the different systems, so here we introduce another kind of alternative or current system we call grid arrow. So like it's using in one of the village water solution in rural India. So this is a current solution which provides reverse osmosis technology provided by on-grid electricity. And in India, because most of the generation still rely on coal-based generators, so we can say this one has relatively high emission, and we use like solar-based technology, which like if we don't consider the embodied emission, operational emission is almost zero. By making the ED technology from constant to more and introduce water storage and making it very flexible, we can consistently reduce the cost and remove the cost of the battery storage. As a result, the lifetime cost of the water could be almost even a little bit lower compared to the current kind of very high, relatively high emission solution. So we can we make the technology cost effective at the same time we minimize emission. So the conclusion is quite high level. So in the first one, the energy storage performance cost lead to a different system optimization result, but the data, availability is unequal, and also they are fully available and available across different technologies. The second one, like co-delivery of energy efficiency and electrical flexibility, can create opportunity, to reduce the cost without using, kind of the advanced or more energy storage technology. So that's all from me. Thank you.
Can I start with a question?
Sure.
Yeah. A couple of years ago, we worked on a proposal for agrivoltaics for Africa.
Yeah.
Okay. One of the main points was desalinization of water there. How ready is this technology to go to the field for I don't know, real use cases and implementation? Remember Africa, sometimes the temperature, the weather demands the specific conditions on the hardware and implementation.
Oh yeah, I think that the system I mentioned here, so both systems are tested in the real environment. So this one will test in Mexico. They're also very harsh environment. Yeah. And this one, the first one will test in India. So I mean, probably not as hot. I'm not sure, but it's also very hot and harsh environment compared to the kind of the well-controlled environment. And then from the other point of view, like all the system there, so even for this new more advanced innovation here, all the components are commercially available. So because our research or innovation more about how to operate the system rather than how to design a new system. But I would say from supply chain perspective, so everything commercially available, and we also tested in the real environment. So during the period of testing, there was no major issue, but it's still a new technology, still a new way to operate it. I would say that how good it is over a very longer term, so still need to be tested. But in general, compared to other technologies, practically this one could be deployed probably immediately, and you can through the time you can know better how to perform with probably years or 10 years to see how it degraded. But that's also something we need to take care of over the time.
Okay, perfect. Just one second thing, very fast. Every time we deal with desalinization, we had problem with the water contamination, heavy metals and all the kind of contaminants you can find there. Do you guys address that somehow?
Short answer.
I think it's kind of out of scope.
Yeah, short answer is no, because this technology is mainly about remove the salt dissolving the water. And if you have more contamination, for example, I think there will be the pre-treatment to make sure, like if we can add pre-treatment to deal with some other contaminants or like larger particles, right? And also we may have another post-treatment to kill some kind of bacteria, that different contamination in the water. But this one mainly for example to remove the salt in the water.
Okay, perfect. Thank you. Any other questions?
Yes. I'm interested in the compressed air energy storage. Can you just sort of maybe summarize the state of the art? Is it adequately modeled, or are there research questions about that need to be understood to make it more accurate? In terms of the physical model.
I think if we talk about physical model, so there are always room to improve. But I would say depending on what accuracy you satisfy with. So I can give an example. So for example, I think I can give an example. Like for example, the point here, there are several companies that are kind of building the 100 megawatt-hour system. So we use some kind of public data to validate our model. I didn't show here. We try to. There are some from several kilowatt-hour system published in literature. We also related one parameter. We have really good validation compared to experimental data. And for the other companies, they also have their in-house model to design optimize the system. So I think there is a company in Canada that are building kind of the 100 to 300 megawatt system. Probably it's still ongoing. So in China, they probably have several, I mean, I can't remember exact number, but at least they have 3 to 5, like over 100 megawatt hours compressed energy storage system has been built in operation or almost, close to nearly operational. So I would say the model could be relatively ready or almost ready or already ready, to build system and make it operational and start to provide service, to in real world application.
Thank you.
Thanks a lot for your presentation. I also had a question on compressed air energy storage, more so on the scale, the scale of this technology. Like, what is the current status of, like, is it viable at distributed scale or like decentral scale for community projects or microgrids?
Yeah, I think that's a good question. And currently in the presentation, I almost heavily focus on the grid scale, something like 100 megawatt. But there are also like smaller scale compressed energy system. I think technically definitely can provide smaller scale, but we probably only need to care more about the commercial viability, because in the probably 10 years ago, there are very two famous like company in the US. They provide smaller scale compressed energy storage, and then just disappeared due to the cost reduction of the manufacturer. But for compressed air, so in the UK, there's a company they are building. They provide service to they call the edge of the network. So basically, they provide their innovation using also at the back. So you use some energy storage, compressed air, you can retrofit the diesel engine as a compressor and expand the turbo turbine. So they try to achieve the low cost and they try to address the network congestion rather than the grid scale arbitrage kind of electrical services. So they provide the flexibility to the network. And also there are another several applications where battery may not be suitable and a relatively smaller scale. So for example, in offshore environment, so there are like offshore renewable energy storage, they put the tank of compressed air under the water, which make it very robust, more robust than the lithium-ion battery. So there are kind of the research and also the kind of entrepreneurship around the smaller scale compressed air across the world.
Yeah, thanks for great talk. So I see for desalination, you convert like solvent into electricity first, and then do desalination. There's also this technology that converts solvent directly into heat and use that to localize water evaporation.
Yeah.
But that technology has been there for a while, but I don't know if anyone tried to implement it. Do you think that's still a promising routine, or there are some
Yeah, I think we also did do kind of review and analysis of different type of solar design technologies. I think for the localized solar thermal distillation kind of technologies, I think it's very, I guess like I would say like by nature, they probably have entirely different production rate. So those kind of localized thermal based technology, probably the production rate is relatively small compared to what we are looking here. So I think that's based on thermal energy and the latent heat, that's a theoretical barrier potentially to produce a lot of water. And I think that I know there are some companies and research groups working on commercialization of those technology for probably like house-based solution rather than what we are focusing here. It's more like larger scale, like for thousands of people for a village. So I think depending on different products, different scale of the water production we are targeting. So the technology could be, the most suitable technology would be different as well. For the localized thermal storage, thermal desalination, I would say probably the target market, the target user case will be more likely around the smaller scale, like personal or like house-based water solution, rather than larger scale like community or like city-wide water desalination technology.
Anyone else? Thank you. Okay. Now we have two papers here from, yeah. Maya, yeah.